welcome to my talk. It's a virtual talk. If you're going to be in Vienna, come see me in person, probably will be better. Presenting work on inferring the long-term causal effects of long-term treatments from short-term experiments. Joint work with a bunch of my co-authors also at Netflix. Let's talk a bit about the motivation. So long-term outcomes often are of primary importance. So you think about in a medical setting, we care about health outcomes over time. At businesses such as Netflix, we care about long-term revenue as opposed to, say, short-term revenue. But one strange thing is that tests are often short for many reasons. Even when we explicitly care about a long-term treatment, so just to define long-term treatment, it's continuous exposure, so not a once-off, but continual, to a novel intervention that extends beyond the length of the experiment. So at Netflix, for instance, I like to think of a permanent change to a recommender system. And the question really becomes, how can we measure the causal effect on long-term outcomes from this long-term treatment, even when experiments are very short? If you're aware of the literature, you'll be aware of the work on surrogates. So surrogates are short-term proxies for long-term outcomes. And so in that work, there's a common assumption about surrogates, which is that the surrogates will mediate the entire treatment effect. So in the left-hand case, figure A, we have the treatment, here W, going through the surrogate, and then the surrogate affects the outcome. We're talking about long-term outcomes here. So note that the treatment does not directly affect the long-term outcome. Now, if we think about long-term treatments, so continual exposure over time, so we're going to see a surrogate at some intermediate time period, and we're going to see continual exposure to this treatment, which by definition means that the treatment has to affect the long-term outcome. So by definition, the surrogate will not mediate the entire treatment effect. So in that sense, the surrogacy assumption won't hold for long-term treatments. So a preview of the paper, we're going to provide a method to estimate these long-term causal effects from this long-term treatment, given that we only have a short experiment. So crucially, we're not going to assume anything about having a surrogate or a valid surrogate. And also there's going to be no need for an observational data set. And there's going to be basically 3 sections to the paper. First up is identification proofs and the assumptions required for identification. We're going to end up with the estimand long-term treatment effect being the difference in Q functions from offline reinforcement learning. Estimation, we're going to basically borrow a doubly robust, asymptotically efficient estimator, again from offline reinforcement learning, which basically follows the standard route through double-ML. And then we'll have simulation details and results. There's also code available. The simulation is based on a sepsis simulator. Before going into the gory math, let's work on just some intuition via pictures. Hopefully this works for some of you. So this is a character from Stranger Things. Her name is 11, and so this is 11 in the various states in the show. So technically it's 11 in season 1, 11 in season 2, 11 in season 3. There are binary actions, so treatment and control, a whole bunch of transitions between states, and technically these should also change depending on which action is taken. And then there's also rewards per state and action. So I like to think of this as season 1, 11's very happy. She's very angry in season 2, this version, and this one she's like laughing out loud, which doesn't match the picture. But as in standard Markov decision process, what we care about are kind of like the long-term rewards. So it's basically the sum of the rewards here. The rewards are a function of whether the age, in this case 11, received treatment or not. There's some discounting, which is gamma raised to the power t, and this term here is just a normalization factor, which normalizes everything to basically a single time period. Now, if we wanted the long-term treatment effect, like I said earlier, we'd just run a long-term trial or A/B test. So here, and suppose we just care about the long-term outcomes when 11 starts from season 1. So we have like twin versions of 11 in season 1. So one that receives the treatment, one that has the control. So we just watch her evolve over time and do the long-term treatment. So again, continual exposure, and then do the same thing for the control, and basically accumulate the rewards. So this first half here is like the treatment cumulative rewards discounted appropriately minus the control cumulative rewards. Ideally, we'd have many versions of this. We wouldn't just have like 2 people through this experiment. We'd take the difference, or expected difference, we'd get the long-term average treatment effect. Like I said earlier, we're not going to be able to do that. Otherwise, there's no point in this paper. But suppose we only had the ability to run a short-term test. So this is basically the core idea of the paper. So what we can do is basically run a short-term test, but on everyone. So notice that these are all the states that exist in this world. So we get all the people, all the versions of 11 in this world, give them treatment, watch them evolve, and do the same thing, start off with the same states, so get their twin versions of those states that we're interested in, give them control, watch them evolve. And so that's basically a 2-period test, so very short. Given those results from the short-term experiment, we can actually mimic a long-term trial by stitching together the results from the short-term trial. So in particular, if we make a Markov assumption, we can basically just stitch together the short-term transitions from period 1, period 2, and period 3 to basically like synthesize a long-term outcome. Again, we'd have many transitions and many people, ideally in the treatment control arm. So this averaging will average across the randomness in this. But then what we're basically doing here is we're saying the long-term difference in cumulative rewards is basically the difference between 2 Markov chains, or difference in the cumulative rewards from 2 Markov chains. And so what we can also do is we can also, using this idea, think about, instead of just a literal continual exposure long-term treatment, so the treatment forever, we can do things where we say, okay, what if we care about treatment for 2 periods, then control? So again, stitching these things together appropriately, we can basically generalize to any duration treatment regime from a single experiment. So one challenge I'll say is, like, before I explain these things of Markov chains, once you start thinking about there being actually actions, so in this case you're thinking about a treatment policy of action, control, or treatment, control, we need to start thinking about Q functions as opposed to vanilla Markov chains. The basic idea is to fit a Markov chain on treatment, and then separately a Markov chain on control, and difference the cumulative rewards. Now, in practice, we're not going to be able to do that for a number of reasons. Firstly, we need the Markov property to hold, and for that to hold, we need a large state space. And once we have a large state space, the curse of dimensionality is going to hit. Secondly, states are continuous, so unless we're willing to discretize our state space, we can't even form a transition matrix. And finally, as I alluded to earlier, if we want to evaluate different treatment durations, we're going to need to use Q functions, and so that moves us away from just a vanilla Markov chain. So the solution, the one we'll use, is to work with Q functions, and moreover, machine learning based function approximators, as we don't want to explicitly form the transition matrix. And what they'll require is borrowing some machinery from the offline reinforcement learning world, where there's existing asymptotic efficient estimators, in particular being doubly robust to the various nuisance functions such as the Q function that we have to estimate. Now that I've explained why we need to move beyond vanilla Markov chains, let's go through the slightly less gory, but not actually gory math. And so we'll start off with the estimand. It's going to be a difference in long-term potential outcomes. Notice that it's indexed by this cap T, which indicates that in this case, we're interested in a treatment policy that lasts for T periods and then just switches off afterwards. So that's going to be equal to the expectation of the potential outcomes under this policy where we have treatment on for T periods and 0 afterwards, and then minus the potential outcomes under the control policy. Now the first assumption we're going to make is one of additive rewards. So it's basically saying, I think I said this earlier, that the long-term outcome is decomposed into basically per period rewards with some discounting and a normalization factor out the front. So this is the full list of assumptions. I already talked about assumption 1. Assumption 1s, 2 and 3 are, I would argue, relatively uncontroversial. We're making a lot of work from assumption 4, the Markov property, which is fairly standard but is new in terms of long-term causal inference. And finally, like all work where you're extending estimates beyond the period of measurement, we have to make a stationarity assumption. So our estimate depends heavily on this policy pi t. Again, sets a equals 1 for T periods and 0 thereafter. That policy is non-stationary because it depends on T. Now, that's going to mean that the Q function is going to inherit this non-stationarity, and it's a huge pain to estimate non-stationary Q functions. So what we're going to do instead is we're going to look for an equivalent stationary stochastic policy. So stationary means it doesn't depend on T, and you can show that a good approximation of that equivalent stationary policy is going to be equal a policy that sets the probability of receiving treatment to 1 minus gamma cap T. Just to quickly work through some intuition here, the always on treatment policy where T is equal to infinity, gamma to infinity is equal to 0, so that's going to be the probability of receiving treatment is 1. We can do the opposite, the control policy as well, where we never give anyone the treatment, which is T equals 0. So gamma to 0 is 1, so 1 minus 1 is 0. So in that case, the probability of receiving treatment is 0. Now with that stationary policy, we can write a stationary Q function, and then given this stationary Q function, assuming the assumptions 1 to 5 from the previous slide hold, we can write the estimand, which is the long-term treatment effect of this like T duration policy, is basically equal to the difference in Q functions. Now that we have identification where our long-term treatment effect is equal to the difference in Q functions, we need to talk about estimation. So what we'll do is basically pursue this route via double machine learning, where we're going to derive the efficient influence function, basically use a naive estimate with a debiasing term derived from the efficient influence function. So I'm not going to walk through all of this besides like going to kind of the end, which is the final form of the estimator is the difference in Q functions plus a debiasing term that relates to the efficient influence function. And we don't prove it in this paper, but we cite the relevant literature that this estimator is root n consistent asymptotically normal, so you can easily construct confidence intervals, and doubly robust to the nuisance functions, in which case here they're going to be the Q function, and W, which is the density ratio function, which is described in the paper. So let's look at some experiments. So again, we care about a treatment policy where the treatment is applied for T periods. So I'm going to run a bunch of experiments where we vary this cap T from one period to infinite periods. And keep in mind, we're always going to calculate the long-term ATE, both when we have the ground truth and also for when we're comparing estimators. So what's varying in time is the treatment duration, and we're always calculating the long-term average treatment effect. For our method, the offline reinforcement learning method, we're going to give it 2 periods of data, so to mimic a short-term experiment, and we're going to compare it against the surrogate method. So to get the surrogate method off the ground, we're going to give it an observational data set, which is basically a whole bunch of trajectories under control, because again, long-term treatment, we're assuming it's a novel treatment, it's a new one. New treatment only exists in the experimental data. And then we're going to give it basically a surrogate at the second period, and also I'm going to run a variant where the surrogate method gets a surrogate far enough in the future for the surrogate assumption to hold. And so if we look at those results, so this is a toy MDP, just to give you a flavor of how these experiments work. So again, we have the duration of treatment extending over time. So if we look at, say, this 24 here and just look upwards, basically this is saying we're comparing estimators where the duration of treatment is 24, and we're calculating the long-term average treatment effects here. So the average treatment effect is this red one here, so it's right there. If we look at the purple line, which is where the surrogate index method gets enough data, so 24, they see a surrogate in the 24th period, a surrogate method works. So this is to say there's nothing fundamentally wrong with the surrogate index method, you just need a surrogate far enough in the future. The offline reinforcement learning method, our method, basically gets pretty much right on accurately here. And if you look at the surrogate index method, where you only get a surrogate, the surrogate variables like very early on, notice that there's basically huge bias. And so if you think about this, what's going on is, if you know the surrogate index method, there's no sense of you being able to control what duration treatment you care about when you're doing the surrogate index method. You basically say, here's my surrogate, I have a short-term data which treatment was on, and it led to this surrogate. Tell me what happens in the future. There's no sense which you can say, I care about a long-term infinite horizon treatment, or I care about a one-period treatment. All the estimates are the same. And so what it actually is estimating is treatment up until the surrogate is observed, and 0 afterwards. So it's like an implicit assumption with the surrogate index method, where it's really estimating kind of long-term effects from a treatment up until the surrogate is measured. Now we can also look at more quantitative results. And so this is a sepsis simulator where we have 2 treatments, ventilation, and then ventilation along with antibiotics. The long-term outcome here is survival. And so if you look at, let's look at the true AT for ventilation or antibiotics. And so I think the durations here are something like 1, 6, 24, 48, and infinite, so the same in the previous chart. The true AT is increasing, which is basically saying the longer you do the treatment, the greater the effect is. Our method does pretty well at the longer duration treatments, less good at the short duration treatments. Again, because our stationary policy is just an approximation, but again, you don't need our method if what you care about is a one period treatment. You could use the surrogate index method because you're going to be able to get a surrogate in one period. If we look at the ventilation treatment, our method is also approximately correct, but in this case, confidence intervals are basically all around 0, so nothing really is happening here. You will notice that you don't get everything for free because the confidence intervals of our method are much larger, although in this quantitative example, for the treatment that actually does something, they're significantly different than 0. Okay, so like I said, come see me in person in Vienna or my co-authors. Happy to chat. Happy to chat about anything. There's a poster session, there's an oral session. Happy to talk in both. Thank you for your time.